today's date. By the end of this lesson, you should be able to state and apply the intermediate value theorem and the mean value theorem. Let's start with the statement of the intermediate value theorem. This is going to be very technical, and then we're going to rephrase it in a little more English-friendly way. So, if f is continuous on the closed interval a to b, f of a does not equal f of b, and k is any number between f of a and f of b, then there exists at least one number c in the interval a to b, that's for x, such that f of c equals k. Another way to say this if f of x is continuous on the interval a to b, and this is x values, the curve must pass through every value for y between f of a and f of b at least once. Now the key thing here is this is only true if f of x is continuous. So this is really, really, really important. Let's do a little diagram of that. I think that'll help it be clearer. So let's say we've got some value a, some value b. This is on the x-axis. And this is f of a, just some value. And this is f of b, so some value right there. What this is saying is it's saying that if this is continuous, then in order to get from this dot to this dot without lifting our pencil, we have to go through every value in between here. So if I pick some value, k, no matter how I twist and strain, as long as this is a continuous function, at some point there's some value c for x, that when x equals c, y equals k. That's what it's saying. No matter how we strain and strain and strain and strain, if this is a continuous function, we've got to go through all of these numbers here. All of these have to get hit at some point. Now, it may be the case that the curve passes k multiple times. Let's say we've got our same little drawing here. Maybe the function goes like this, woo, woo, and goes something like that. That's entirely okay. Notice that this says at least once. The big thing, though, is that this is not true if f of x is not continuous. So in that case, let's say we had something like this. This number k there's no value between a and b at which y equals k. Okay, this is spiffy, but why do we care? The intermediate value theorem is particularly useful for narrowing down where the zeros of a function are. If a function is continuous, and f of a is less than 0, and f of b is greater than 0, or vice versa, then f of x must have a 0, for some x on the interval a comma b. So for example, let's say that this is a, this is b, we have this dot here, we have this dot here. Somewhere, if this is a continuous function, there's got to be a 0 somewhere. We don't know if it's here, we don't know if it's here, we don't know if it's here. This could, remember, there could be multiple zeros, it could be looping up and down like that. But there's got to be a 0 somewhere in here, because if this is a continuous function, there's no way to get from a negative value for y to a positive value for y without at some point going through 0. And so this was actually used before there were more exact techniques to just kind of narrow down where a 0 was. Because basically it would just take numbers that were closer and closer and closer and closer to each other, and if one was negative, one was positive, there had to be a 0 in between. And just kept doing that until mathematicians got the precision that they wanted for the 0. And being able to find zeros is very, very important in the graph analysis unit, because zeros of a derivative are going to be used to tell us when we have a maximum and minimum for a function itself. And this is something that is incredibly useful in real-world situations. Let's use the intermediate value theorem for a couple of problems. Use the intermediate value theorem to show that the polynomial function f of x equals x cubed plus 2x minus 1 has a 0 on the interval 0, 1. So a key thing to know, a polynomial function, polynomial function, a polynomial function by definition is continuous. A polynomial function is really just something like this. f of x equals 3x to the fourth plus 2x squared minus 5x plus 1, or something like that. It's just a polynomial, basically. So we're using the intermediate value theorem to show that there's a zero. So basically we just want to show that one end of the interval is positive, one end of the interval is negative. F of 0 equals 0 cubed plus 2 times 0 minus 1. F of 0 equals negative 1. F of 1 equals 1 cubed plus 2 times 1 minus 1. F of 1 equals 2. Because f of 0 is less than 0 and f of 1 is greater than 0 and f of x is continuous, the intermediate value theorem indicates that for some value x equals c on the interval 0, 1, f of c equals 0. Ta-da! That's it. We can also do similar problems with graphs, or excuse me, with tables, if f of x is a continuous function. And has some values given in the table. Here's x, here's f of x, negative 3, 0, 1, 2, 5, 1, 3, negative 2, negative 6, and 4. What can we conclude about the locations of zeros of f of x? Well, because f of x is continuous, and f of 0 is greater than 0, and f of 1 is less than 0, f of x must have at least one 0. Could have more. On the interval 0, 1. Likewise, notice that when x equals 2, f of x is negative. When x equals 5, f of x is positive. So we've got a similar situation there. There must be at least one 0. On the interval 2, 5, because f of 2 is less than 0 and f of 5 is greater than 0. There may be additional zeros, but these ones we have to have. So like here, maybe f of x is positive at x equals negative 3, negative at x equals negative 2, and positive again at x equals 0. So there might be additional ones, but these are the only ones that we know for certain have to be there. Note again, if we weren't told f of x is continuous, we couldn't conclude anything. Because if it's not continuous, maybe these are the only points on there. Let's do a check for understanding problem with that type. F of x is a function, some values of which are given in the table. One, two, three, actually 1, 2, 4. 3, -1, -5, -4. What can we conclude about the locations of these zeros of f of x? Okay, pause the video, try that one on your own, and then start the video up when you're ready. Okay, turns out this is a trick question. F of x is a function. It does not say anything about whether it is a continuous function. We cannot conclude anything. There may be no zeros at all. Perhaps these are the only 4 points in the entire function. If we were told that it was continuous, then we would be able to conclude that there is a 0 between x equals 1 and x equals 2 because there's a change in f of x from positive to negative here. But if we're not told it's continuous, nada, nothing. Okay, let's turn our attention to the mean value theorem. If f of x is continuous on the closed interval a to b and differentiable very key, there are now 2 conditions instead of 1 on the open interval a to b. Now notice that it's not doesn't have to be differentiable at the endpoints, simply because if those endpoints are actual endpoints, then there is no derivative, there's no single tangent line at that point. But it's okay, it's just got to be in between the 2 endpoints. It is differentiable. It's got to be continuous for the entire interval, including the endpoints. Then there exists a number c, this is for x, in the interval ab such that f prime of c, the derivative, equals f of b minus f of a over b minus a. For the differentiable piece here, really what we're worried about, since we already know that it's continuous, this means no sharp turns. So let's restate that geometrically. This means that if a function is continuous with no sharp turns, if you draw a secant line through 2 points, somewhere between them is a point whose tangent line has the same slope as the secant line. Here's what this looks like. Let's say we've got our little function. Here's A, here's B, f of A, f of B. And there's a nice smooth curve like that. This point we know is the point A comma f of A, and this point we know is the point B comma f of B. And if we draw a secant line right through those, we can find the slope of the secant line by doing f of B minus f of A, that's change in y, over B minus A, that's change in x. So that's this little part right here. Now let's imagine that we just took that and we just moved it up here. At some point, we're going to reach a point right here, let's say, where the slope of the tangent line right there is parallel to the slope of the secant line. So let's say this is the point C, f of C. We know that the slope of the tangent line at x equals c is f prime of c. That's what this is saying. That the slope of the tangent line at this point, somewhere on this interval, there's going to be a point where the slope of the tangent line here is the same as the slope of the secant line for the interval overall. One thing to be wary of, this does not work if there's a sharp turn. Let's say we've got this situation. Here's our little secant line. But we notice that this point doesn't have a tangent line because there could be multiple different tangent lines. There's no single one that we can pin down. And so we really only have these two little line segments. This has a steeper slope, this has a shallower slope, but there is no point that has the exact same slope as for the tangent line as there is for the secant line here. We can also think of the mean value theorem in terms of rate of change. The mean value theorem means there is some point in the interval AB where the instantaneous rate of change so for example velocity equals the average rate of change. So this is actually quite useful for real-world examples. Two patrol cars, so this is like highway patrol, with radar are 5 miles apart on a highway. As a truck passes the first car, its speed is recorded as 55 miles per hour. 4 minutes later, it passes the second patrol car, and its speed is recorded as 50 miles per hour. If the speed limit is 55 miles per hour, should the driver get a speeding ticket? So go ahead and think about that one for a second. Okay, so let's look at this. At first glance, when the first patrol car uses the radar, then the speed of the truck is 55 miles per hour. The second time around, it's 50 miles per hour. So it seems at first glance like the truck is good to go. However, let's draw this out and let's look at something. So here's our little road. And here's one little car. Little lights on top. Woo. Here's the other little car. Lights on top. There we go. We know they are 5 miles apart. Now, one of the things that's hidden in the problem here is that it takes the truck 4 minutes to go all this distance. So that means that the average speed of the truck between patrol cars is 5 miles in 4 minutes. Now, we're working in miles per hour earlier, so that means we should convert these minutes, 60 minutes, in 1 hour. So 5 times 60 divided by 4, 75 miles per hour. Now, the mean value theorem and we assume the truck is not able to teleport, so it is continuous. And because it's impossible to change speed instantaneously, the derivative, the velocity, also needs to be continuous, even if it might change quickly at some point. The mean value theorem indicates that at some point, well, really time, between the first car and the second car, the truck's instantaneous speed must have been equal to its average speed over the interval. So the truck should get a ticket because at some time its speed was 75 miles per hour, which is well over the speed limit. And in fact, because this is an average speed, that means that at sometimes it was probably going slower and sometimes it was probably going faster. So she really get a ticket because it's probably going even faster than 75 miles per hour at some point. But this would hold up in court because we know that at some point it was going exactly 75. That's guaranteed by the mean value theorem since all conditions are met. And 75 is way over 55. So let's look at another sort of more pure mathematical example with this. The value of C that satisfies the mean value theorem, value There are other mean value theorems, so this is the one we know. On the interval (0 to 5) for the function f of x equals x cubed minus 6x is what? So first we have to remember what the mean value theorem is. Mean value theorem means that f prime of c equals, in this case, it's going to be f of 5 minus f of 0 over 5 minus 0. So we can find f of 5. That's going to be 5 cubed minus 6 times 5 minus 0 cubed minus 6 times 0. 5 minus 0 is just 5. So this is 125 minus 30 all over 5. That is 95 over 5, or 19. So that means our problem is to find f prime of c such that, find c such that f prime of c equals 19. So we're going to be working with the derivative, so let's start off with our original function. F of x equals x cubed minus 6x. F prime of x equals 3x squared minus 6. And we want f prime of that to equal some number, 19. So 19 equals 3x squared minus 6. Add 6 to both sides, 25 equals 3x squared. divide both sides by 3. X equals the square root of 25/3, or 5 over root 3. This is plus or minus, this is plus or minus. However, notice that we are only want a number between 0 and 5, so that means we have to have a positive number. So that means x equals 5 over the square root of 3. The intermediate value theorem and the mean value theorem are what are called existence theorems. They just say that something exists. There are some other existence theorems, and we're going to look at one, the extreme value theorem. This one is not used quite as much, but it's still a good one to know. If f of x is continuous on a closed interval, here we're back again to just continuous, but here the keyword is closed instead of continuous, a comma b, then f of x has both a minimum and a maximum on that interval. This is why it's called extreme value theorem, minimum being the lowest point, maximum being the highest point. However, there are very specific definitions for minimum and maximum, and they may be a little bit different than you might think. F of c is a maximum on the interval I if, so this is a maximum, f of c is less than or equal to f of x for all x in I. Notice that there is a little or equal to symbol. And we'll see in a graph in just a minute why that matters. Similarly, f of c is a minimum on the interval I if f of c, maximum should be greater than or equal to if f of c is less than or equal to f of x for all x in I. There we go. Note this only works continuous functions on a closed interval. So what this is saying, let's say we've got a little function like this, goes down like that. Here we've got a maximum, here we've got a minimum. However, if we have an open interval, there's no maximum. Basically, this open interval simply means that this single point is not defined, but we do have other points getting infinitely close to it, and since it gets infinitely close, we can't settle on a single number. We do still, however, have a minimum. Continuity also matters. here our maximum is back, but let's say we have an open circle there. Discontinuous, no minimum. Still have the maximum up here though. There's also one that it might be a little bit counterintuitive. This is a constant function. All the points here are both minima and maximum, and the reason for that is because of this little equals sign that's under these two. Because this means that these are always true as long as we have that little equal sign, so that even in these situations there's still a maximum and minimum, it's just all points. Okay, let's look at some problems that combine all three. The function f of x is continuous on the interval 3 to 9 and differentiable on the interval 3 to 9. It's an open interval. F of 3 equals 1, and f of 9 equals -1. Must there exist a value c in the interval 3, 9 such that each of the following are true. So for the first problem, we're going to look at f of c equals 0. Does this have to be true? So pause the video for a second, look back at your notes, think about that, and start the video again when you have your answer. So f of c equals 0. We're talking about f, so we'll be looking at the intermediate or the extreme value theorems. We wouldn't be looking at the mean value theorem. So we know that f of 3 is greater than 0, f of 9 is less than 0. So as long as f of x is continuous, then there has to be a value for c, for x, such that f of c goes through all of the points between them. So since 0 is between -1 and 1, yes. Okay, for part B, does f prime of c have to equal -2? Think about that one for a little bit. So restart the video when you're ready. We're talking about f prime, so that means we're going to be talking about the mean value theorem. F of x is continuous and differentiable. So the mean value theorem applies. F of 9 minus f of 3 over 9 minus 3, that equals -1 minus +1 divided by 6 equals -2 divided by 6 equals -1/3. So no, the mean value theorem says there's a C such that f prime of C equals -1/3, but it says nothing about -2. And for part C, must there be a C such that f of C is less than or equal to f of x for all x on the closed interval 3 to 9. Okay, think about that one for a second. Restart the video when you're ready. Okay, this is talking about the extreme value theorem. F of x is continuous, so the extreme value theorem applies, and yes, there's got to be a minimum. That's just what the theorem states. Okay, for our last problems, we're just going to imagine something was different about these. This is 4. If f of x were not differentiable, in question 3, would A, B, and C still hold true? So remember, for part A, that was the intermediate value theorem, B was the mean value theorem, and C was the extreme value theorem. A and C, only require continuity, so they would still be true. B requires differentiability, so it would not hold true. I guess in this case, since we saw that this wasn't true to begin with, it's still not true. But really the key thing is that if we're going to work with the mean value theorem, we have to have differentiability. Similar note, if f of x were not continuous, would A, B, and C still hold true? And none of them would be. Continuity is required for all three. That concludes these notes.